Okay, today we're going to do right triangle trigonometry, finding the missing angle. Before I do that, though, we have to teach you about arc sine, arc tangent, and arc cosine functions. And in order to do that, we need to talk about inverse functions. So I'm going to do some old problems that you know how to do really well. Let's look at this first problem. 2x equals 10. So I say to myself, how do I solve for x? I know that x is being multiplied by 2, so I'm going to do what we call the inverse function to multiplication. So the inverse of multiplying is dividing. So I'm going to divide both sides by 2. And of course, you know how to solve the problem from there. In problem 2, what's being done to x, right? There's no parentheses here, but it's kind of understood. X is having this parentheses squared done to it, right? That's the squared function. So it's having the squared function applied to it. How do I undo something being squared? Well, I don't divide, I don't multiply, I don't add or subtract. The inverse of squaring is square rooting. So I'm going to square root both sides of the equation. Why do I do that? Because when you have something squared and then immediately square rooted, you get back to the original, which is x. Okay, over here, back to problem 1. When I have something being multiplied by x and then I divide by that same number, what's left? Just x. See, the idea is to get x by itself. So to undo whatever operation is being done, I do what's called the inverse operation. So the inverse of squaring is square rooting. And that's why I get an x here. And of course, I get a 4 here. Of course, remember, it's plus or minus 4. We've talked about that. And in problem 3, if it's a pretty simple one, what's being done to x? It's being added, or it's having a 6 added to it. So we have to do the inverse of adding, which is subtracting from both sides to get x by itself. Okay? In every case, we get x by itself. That's the key. And to get x by itself, you have to inverse whatever's being done to x. Okay, that's really important for today's lesson, which is trigonometry, finding the missing angles in a right triangle. Okay? All right, so I'll get back to that and I'll reference that in a few minutes. But let's first take a look at this triangle. So I have a right triangle. That's important. It can't work without a right triangle. Trigonometry can't. Or this right triangle trig can't. And I have two sides. So in the previous problems we've worked on, we've had an angle and a side, and we're looking for another side. But in this case, I've got two sides. And I could find the third side, by the way, pretty easily. And that would make my life a little bit easier. But sometimes it's going to be a radical, or it's going to take a little more time, and we don't really need to worry about it. But that is another way you can do this problem. Although regardless, we're going to end up using the inverse that we're going to talk about in a second. So in this problem, this theta or angle A or angle CAB, by the way, there's multiple names for this angle, right? There could even be an X in there. We don't usually do that, but we usually use theta for our variable, but there could be an X in there. Anyway, I'm looking for the angle, whereas before I've always known the angle. So in the previous problems, I've had a 35 here or a 28-degree angle here, and I write my trig function, or my trig ratios, and then I figure out which one I want to use. Well, we're going to do the same thing here. Okay, and like I said to you, I like to teach it this way because you'll eventually see the pattern yourself and you don't have to go through all of the work that we're about to do. But it's good to do it as practice and until you figure out the ratio rather than me trying to explain each time how to, which one to pick. Okay, so there's 3 trig ratios. Don't forget, we've talked about them many times. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, so we're going to write all 3 trig functions for this angle. Now I could use a or theta, by the way, it doesn't matter. So I could write sine of theta, which I'm going to use. Okay, but I could also write sine of a. That's also correct. I could even write, well, I don't think we usually ever do it, but you could write sine of angle CAB, but it's just a little too much writing. So we're going to start with sine of theta, okay, and then I'm going to ask you what is the opposite and what is the adjacent. Okay, so the sine of theta equals, right? Remember, there's kind of a parenthesis. We don't write it very often or often enough, but there's a parenthesis here. It's really sine of, and remember, sin is short for sine. It's an abbreviation for sine, S-I-N-E. So it's really the sine of theta, kind of like when I do theta squared. See, so I'm doing this parenthesis, kind of like showing me I'm doing an operation on theta. See. Or even if I did the square root of theta, though we don't usually use parentheses, the calculators or the old calculators used to put in parentheses like this. I'm square rooting this group, theta, see? But we often don't write the parentheses because it takes extra time and it's kind of understood, but you should know that it's there. So the sine of theta is, of course, a ratio. So it's the opposite. So the opposite is across from it, right? The opposite is here. And the hypotenuse, which is always across from the right angle, is here, right? So it's opposite over hypotenuse. Now, why am I leaving the top blank? Because I don't know what it is, right? There's kind of a question mark here. I could have found it using Pythagorean theorem if I want to, and then I could go from here. So when you look in this problem, I'm going to show you that the sine ratio is not the one we're going to use because we have one unknown there and we also have another unknown here. There's no way to solve an equation with two unknowns like this unless we had another equation, okay? So these two unknowns mean we're not going to be using sine, but it's okay to write it. I'm going to write all three, and I'm going to get in the habit of writing all three. Cosine of theta. Well, that's the adjacent over the hypotenuse. So the adjacent is this leg because it's right next to it. It's touching the angle. So that's 6 over 9. And that I can solve. So I would stop here normally. But I'm just going to teach you how to write the third one. Or get in the habit of writing all three in case I needed it. So the tangent is the opposite over the adjacent. So it's going to be the question mark over 6. And again, you can see in this problem here, here we only had the one unknown, right? Although I want to make that yellow. So here we only have the one unknown. But in this one, we have two unknowns. So in sine, right, and tangent, we're not going to use them because they're not going to help us. We need the equation that has only one unknown. Okay, so this is all kind of review. The only difference that we did before is you had a number here with this theta. You had a number right there, and then one of these was a variable, and you knew how to solve that, okay? But in this one now, and I'm just going to bring it down, we don't have a number here. So we have to get theta by itself. So before, for example, we may have a problem like this, cosine of 28 equals x over 10. And you're like, oh, what's being done to x? It's being divided by 10. Oh, I know what to do. I do the inverse operation of dividing, which is multiplying, and then I solve for x. And of course, x is 10 times the cosine of 28. So that's what we used to do, right? But here, something's being done to theta, and it's not being multiplied. It's not being divided like it was over here. It's being cosigned, right? It's being cosigned. So in other words, you're taking the cosine of theta, and you don't want it. You want it to end up like this. You want to know what the angle is. So I want to know what theta is. I want to get the variable. We always want to get the variable by itself, right? In this problem here, I'm trying to get x by itself. In the problems on the other page, we're trying to get x by itself. We're always trying to get the variable by itself. So I'm trying to get theta by itself. So how do I undo the cosine of theta? Okay, well, it actually turns out to be a function called the arcsine. Sorry, not arcsine, arccosine in this case. For sine, it would be arcsine. So for sine, it would be arcsine. For cosine, it would be arccosine. And for tangent, it would be arctangent. Now, I'm actually not going to write that because it's just going to complicate things because your calculator doesn't use that. It uses a generic inverse notation. So I'm not going to mention arcsine, arccosine, and arctangent, or I'm certainly not going to write it again. But that's actually the name of the inverse function to sine, cosine, and tangent. Okay? But instead, we're just going to write the generic form, and I'm going to change the color here to help us see it. So I'm going to write cosine of -1. It's not cosine of -1, I should say. It's the inverse cosine. So I'm inverse cosining this blue cosine of theta, and that's going to undo it. So just in case that's messing you up a little bit, I want you to go, and I got to do it to both sides, by the way. So let's fix that before I go to the other slide, because I never want you to like write it on one side and not the other. So I need some space here, and I'm going to write cosine -1, but it's really inverse cosine of that. Okay, so what I did is I inversed cosine both sides. Technically, I arc cosine. That's the official name. But this is a generic way of writing the inverse of something. So I'm doing the inverse of cosine. And the reason why we're using this generic form, as I mentioned earlier, is that's what the calculator uses. So it just makes it easier for you to follow this. But you should know, or at least be familiar with, the fact that I'm technically doing arc cosine on both sides. Now, why am I doing that? Because if you look over here, exactly what I did here. See, I had x being squared, so I did the inverse of squaring, okay? And the inverse of squaring in this case, is the square root. Okay, in our problem, we're just going to leave it as what we call the inverse of cosine. So what happens when well, back to this problem here. What happened when I square root the square? I just get the variable by itself. See, so it's going to happen here too. So here what happens when I inverse cosine the cosine of theta? Well, the inverse and this function, and its original function here, right? The inverse of this function and then the function leaves just theta. So you get just theta by itself. Okay, does everybody follow that? So that's really important. So, but what about the right side? Well, we're going to do this operation called the inverse cosine of 6/9, and that's going to require a graphing calculator. So make sure you have a graphing calculator out. I'm going to bring mine on screen for us. So again, let's talk. We've talked about this many times. Make sure you press mode, and you go to the third one here and make sure in degrees. See, by default it's in radians, so mine wasn't. So I'm going to scroll over, hit enter, and select degree. Okay, once I've done that, you can just quit to get the screen back to the way you normally want it. Okay, it's very important. It should say degree up here too. So what is this operation? It's actually a key on the calculator. So if you look right here, if you look right above the cosine key, hopefully you know where the cosine key is. You've been using it. There's cosine -1, see in blue. So that's a second function. So I have to use the second key to get there, okay? So basically all I'm going to do is type in second cosine, or the inverse cosine. So second, and then if I press the cosine button, I'm going to be actually doing cosine -1 because that's the blue function here. Okay, and there it'll say it on the screen, so you can see it's exactly what I have written here. Cosine -1, or inverse cosine, 6/9. So type in 6 divided by 9, close parentheses, hit enter, and that's your angle. And of course it's going to be off a little bit, which is 48.2. We're going to usually round, sometimes we round to the nearest degree, often, so we would just say 48 degrees. I'm going to do 10th place today. It depends on the instructions that you're given. So it's 48.2 degrees, approximately, right? In fact, if you wanted to be right approximately here, it'd probably be a good idea. All right, that's the answer to the problem. So that's 48 degrees. Now, if they ask you for everything else in the problem, you could find this angle because it's just 90, right? Minus 40, well, 90 plus 48 plus this angle B equals 180, right? So that means these two are complementary. They add up to 90. We've talked about this many times. So this would be 42. That's easy. And you could find this side using Pythagorean theorem, or you could use one of our trig functions, right? If you plug in 48 for one of these thetas, you can find either this one or this one. If you put a 48 in here, you know how to solve this because we've done that last week. Okay? All right, pause the video. Try this problem number 8 here. Copy it down into your notes or on a piece of paper. Try this problem. There is another way to solve this, so if you do know another way, that's okay, but I want you to use trigonometry, then we'll do the other way to talk about it in a second. We're looking for this angle here, okay? But use the trig, so you're going to write all 3 trig functions, just like I did here. You're going to write all 3 trig functions using theta, okay? Sine of theta, cosine of theta, tangent of theta. Write them right here, okay? Pause the video, do that right now, and then I'll show you what I came up with. Okay, so you're back. Let's see what happens. So sine of theta equals the opposite. So that's the side it's not touching, this angle here. That little angle symbol does not touch this side. So that's opposite over hypotenuse. But the hypotenuse is unknown to us, okay? Yes, we could find it. Actually, we could find it pretty easily because there's a special rule we'll talk about in a second if you forgot it. Cosine of theta is the adjacent over the hypotenuse. So you can see we don't have a hypotenuse. So this is going to produce question marks here for these 2 functions. So this is definitely going to be a tangent problem, right? And finally, we get tangent of theta equals the opposite leg over the adjacent leg, which is over here. Okay? So you can see we're not going to use these 2. They're not that they're wrong, but they have 2 unknowns. So we're going to use the tangent ratio to solve this problem. Okay, so we have, and by the way, you can reduce this to 1. Absolutely, I'm going to leave it as 3/3, just for, you know, it might be more of a habit for you to always have a ratio, but you can actually absolutely put 1. The problem will work perfectly. Okay, so good. I have the tangent theta. Now, what do I want to get? My goal is to find out what theta is, right? What the angle is. I want to get what theta is, so I'm going to have to do the inverse of tangent. What's the inverse of tangent? Well, it's technically called arctangent, but we're going to write the inverse. One thing I got to do, I keep moving this 3 over 3 over so I have room. So I just moved it over so I have room on both sides. And I'm going to arctan or inverse tan. We're going to use the inverse version. We're going to inverse tan both sides of the equation. Okay? And that's legal, right? I can do the same function to both sides of the equation. So I'm doing this inverse function. Now, whenever you do an inverse to its original function, just the variable is left, like when we talked about. If you square root a square, or if you square a square root, you're going to get the original variable that was being square rooted or squared. Okay, so this part works out nice, and this part is a calculator exercise. So I'm going to bring my calculator back on screen again. I'm going to clear what I have here, but instead of second cosine, I'm going to use second tangent. That's what this is going to be, right? So I'm going to press second tangent. You could put 1 in here. I'm going to do 3 over 3. Of course, you can type 1. You're going to get the same exact result. You don't have to close the parentheses, by the way. The calculator does it automatically. If you want to be a little fancy or if you're a little OCD like I am, close the parentheses. That's fine. Press enter, and you're going to get 45 degrees. Now, that should come as no surprise to anybody, right? I purposely picked this triangle because this is an isosceles right triangle, right? Both of these angles have to be the same. So it's definitely a 45, 45, 90 triangle. You really do not use trigonometry or do not need to use trigonometry to solve problem 8's missing angle because it's an isosceles right triangle and you should save yourself a ton of work. But I wanted to show you that it does work even for our special right triangles. And of course, this is 3 radical 2, so I could have used 3 radical 2 down here, although the radical does make it a little more complicated when I'm putting it in the calculator, and I have to use parentheses, so you got to be really careful. So definitely better to do it the way I did it here if you're going to use trigonometry. Okay? All right, so for your homework, it's going to be very similar to this, so take a look. You may have a cosine one, of course. Just remember to write this notation on both sides like I did, either sine -1, cosine -1, tangent -1, which is really inverse sine, inverse cosine, inverse tangent. On both sides, use your calculator for this part. Just press second and the trig function that's listed here, plug that fraction in, and you're going to get the angle every time.